Good morning, 7th grader. We'll continue with our lesson, Chemical Transformation, and talk about conservation of mass. The objective that we'll learn at the end of this video is state the law of conservation of matter, or Lavoisier law. First, let's recall back. Certain chemical reactions involve thermal energy or heat energy. Observe the thermometer and try to check what happens for the temperature. Yes, it's increasing. Here, the chemical reaction is accompanied by release of heat. Then the temperature rises. So it's exothermic reaction. While for the second thermometer, the temperature is decreasing and a chemical reaction is accompanied by absorption of heat. Then it's good. It's endothermic, where the temperature is dropping down. Indicate the nature, exothermic or endothermic, of the following chemical reactions. Observe the first picture. The candle is lightened. What do you feel when you approach it? What happens for the temperature of the surrounding? Then it's exothermic. Good. Why for the second picture? Photosynthesis that absorbs heat energy from the sunlight. Then what do we call it? Is it exo or endo? Yeah, think. Yes, it's endothermic. Wonderful. The problem that we faced is, what happens for the mass during a chemical reaction? If I'm changing the reactants into the product, will the mass of the reactant, when they change into product, drop down, increases, remain the same? Let's check what is the change here. To answer, observe the following video carefully and don't forget to take notes. Fill a balloon using a funnel with baking soda and a bottle with vinegar. Place the balloon at the opening of the bottle and using a digital balance, find its mass. Oh, it's 191 grams as initial mass. Now, empty the content of the balloon over the vinegar. Oh, observe the bubbles. The bubbles, do you see? What? The balloon is inflating. Why? Oh, the final mass still 191, where vinegar plus baking soda to give sodium acetate plus water plus carbon dioxide. And upon adding them together, the sign for the chemical reaction is releasing of gas in the form of bubbles. And the mass before and after still the same. Could you name the reactants used in the above chemical reaction? Guess what are they? Vinegar and baking soda. Wonderful. Indicate the role of digital balance. Go back to the physics session. Why do we use the digital balance? Wonderful. To measure the mass of substances. What is the importance of the balloon? Think. Why do we use a balloon? Why do we place the balloon at the opening of the bottle? Wonderful. To trap the released gas. Observe the experiment again and check what happens after mixing the baking soda and the vinegar. Yes, look at it. Do you observe the bubbles and the inflation of the balloon? Good. Bubbles are observed and the balloon inflates, as you see. Do you see the balloon? It's wonderful. Due to what is this observation? Why the balloon inflates and the bubbles are observed? Nice! Due to releasing of a gas. Let's check the digital balances again, before and after the experiment. Do you see? It's 191, and after, the mass is still 191 grams. Now, could you record the mass of the used materials, M1? Yes. What is it? Good. It's still 191 gram. What about after the chemical reaction takes place, which is M2? Wonderful! It's 191 gram. Now, compare the two masses M1 and M2. Don't forget the properties of the word compare. Yes, pause the video and try to compare by yourself. Good. The mass of the used materials at the beginning of the experiment was 191 gram. Do you see the value of the unit? Equal, which is the correct term of comparison here, to that after the chemical reaction takes place, which is 191 gram. The value of the unit also. You are wonderful. Let's check the experiment again. Could you please write the word equation for this reaction by yourself? Pause the video and try. Good. Vinegar plus baking soda, arrow, sodium acetate plus water plus carbon dioxide. What do we call vinegar and baking soda? Give me one word to describe them. Good. They are reactants. What about the obtained products? What do we call them? Yeah, wonderful. They are products. You are wonderful. The total mass of the reactants is 191 gram as shown in the digital balance. And also for the product is 191 gram. They are equal. Then what do we conclude from this? We conclude that in the chemical reaction, no mass is destroyed and no mass is created. And this indicates that mass is conserved. Good. It's known as law of conservation of mass. But how do scientists know that mass is always conserved in chemical reaction? Let's check. Careful experiments in the 1700s by a French chemist named Antoine Lavoisier led to this conclusion. Lavoisier carefully measured the mass of reactants and products in many different chemical reactions. He carried out the reactions inside a sealed jar. Look at the sealed jar. Do you see it? This is a sealed jar as shown in the figure. In every case, the total mass of the jar and its contents was the same after the reaction, which are the products, the mass of the product, as it was before when they was reactants. Then Lavoisier stated the law of conservation of mass or of matter, where Lavoisier stated mass is neither created nor destroyed. It's only transformed or changed during a chemical reaction. There's only changing. Then the total mass of reactants equal to the total mass of a product. If I place them on a Roberval balance, I find that the mass of the reactants are at the same level of the pan of the products. As evaluation 1, calculate the final mass or total mass of the product. Let's check the experiment, where I have a piece of zinc dipped in a hydrochloric acid, and the initial mass was 61.95 grams. Upon reacting them together, hydrogen gas is obtained and also zinc chloride. What about their final mass? Pause the video and try to pull the final mass. Yes? Good. According to the law of conservation of mass, total mass of reactants equal total mass of a product. Then initial mass equal the final mass equal 61.95 grams. I have to mention the unit. Let's take another evaluation where I have 42 grams of sodium hydrogenocarbonate and 24.5 grams of sulfuric acid in the beaker. Upon adding them together, I'll obtain 35.5 grams of sodium sulfate, 9 grams of water, and carbon dioxide with unknown mass in the form of bubbles. Could you calculate the mass of the released gas? Try by yourself. Before we continue, pause the video and try. It's your turn now. Think. Yes, good. According to the law of conservation of mass, total mass of reactants equal total mass of a product. Let's substitute the reactants. What are the reactants? They are sodium hydrogenocarbonates and sulfuric acid. Then, mass of sodium hydrogenocarbonates plus mass of sulfuric acid equal to the mass of the products. What are the products here? Yes, they are water, carbon dioxide, sodium sulfate. Then they must equal. So, equal to the mass of sodium sulfate plus mass of carbon dioxide plus mass of water. Now, let's substitute the values of the masses. Mass of sodium hydrogenocarbonates, as indicated, is 42 grams, substituted, plus mass of sulfuric acid, yes, it's 24.5 grams, good, equal mass of sodium sulfate. What about the mass of sodium sulfate? It's 35.5 grams, I substituted, plus, as you see, mass of carbon dioxide. Oh, I didn't know the mass of carbon dioxide. So it is the unknown and I write mass of carbon dioxide. That's it, as it is. Plus mass of water, which is, yes, 9 grams. I write 9 grams. So I substitute each mass by its value. Now let's add the values together. Before the equal and after the equal to obtain 66.5 grams equal. When I add the values after the equal, I'll obtain 44.5 grams plus mass of carbon dioxide. Now, how could I determine mass of carbon dioxide? By changing the position of 44.5 grams, and don't forget to change the sign. So, mass of carbon dioxide equal 66.5 minus, you see, 44.5 equal 22 grams. You are wonderful. Evaluation 3. Also, you have to pause the video. The following figure shows the reaction between gray iron powder, as you see, this is the iron powder, and yellow sulfur, as you see in the figure. When mixing iron and sulfur, heat is absorbed to produce a black iron sulfide, as you see. Check the values on the digital balances, okay, because we are going to use them, 140, 80, and a question marks. Now, indicate the sign for the occurrence of this chemical reaction. Look at it. When I add iron and sulfur to obtain black iron sulfide, then what is the sign? Good. Change in color from gray and yellow into black. You are wonderful. Name the reactants and the products. What are the reactants here? Yeah, they are the used materials. You are good. Then the reactants are iron and sulfur. What about the products? The obtained substances. Good. They are iron sulfide. We have only one product. Good. You are wonderful. Now observe what happens. We need energy. We need a source of heat. Then is this chemical reaction exothermic or endothermic? Justify. Look at it. We need energy. We need a source of heat. Then the chemical reaction absorbs this energy. Yes, wonderful. It's endothermic since heat absorbed during the chemical reaction, as you see. You are wonderful. Nice. Let's continue for the fourth questions. Write the word equation of the chemical reaction take place. Don't forget word equations. Plus and arrow. Good. Iron plus sulfur. As you see the plus between reactants. Arrow. And iron sulfide as the product. Determine the mass of the obtained product. Also, don't forget to pause the video. According to the law of conservation of mass, these are the digital balances with the values on them. Use them. Yes. Good. According to the law, mass of reactants equal to the mass of the product. The mass of iron plus mass of sulfur equal mass of iron sulfide. 140 grams, which is mass of iron, as indicated on the digital balance, plus 80 grams, which is the mass of the sulfur, equal mass of iron sulfide, the unknown. Then the mass of iron sulfide is 140 plus 80 equal to 120 grams. Now, name and state the used law. Pause the video, and you have to memorize it carefully. Good. Lavoisier law. Matter is neither created nor destroyed during a chemical reaction. There's only transformation.